Continuing on in section 10.2, in example 4, we're going to write a radical expression. A rectangular door in a museum is 3 times as tall as it is wide. What is the simplified expression for the maximum length of the painting that fits through the door? So there's a better picture of this in the book, but the idea here is that the blue is our door and the green is our picture. So some kind of a picture here. Okay, and we're trying to fit it through the door. And we know that if we look at a door, guys, it's going to be a bigger picture that can go through if we go diagonally than if we go straight and up and down. And we know that from a triangle as well, because we know that the hypotenuse of a triangle is always our longest side. So here, we're looking for this distance right here. We know that the door is 3 times as tall as it is wide. So if our width is W, our height is 3W. And here we have a right triangle. So we can use Pythagorean's theorem. A squared plus B squared equals C squared. Our two side lengths are W and 3W. And keep in mind that when we square 3W, guys, that whole thing gets squared, which means the 3 gets squared to 9 and the W gets squared. That's our product property of exponents. And we bring down the rest of our problem. Now I have a 1 in front of my W squared if there isn't a number. So 1 plus 9 gives me 10 W squared. And because my variables are the exact same, I keep them as W squared. To get rid of my square, I take the square root. So I get the square root of 10. W squared is W times W. And to simplify here, I take out that pair of W's as a W, and I have W times the square root of 10 equals C. And that's going to be my length here. We don't know what our width is, so I can't find the exact value or the approximate value, but that's our relationship here. So our width times the square root of 10 would work for this particular door. Same idea here. I have a rough sketch here, but the height is 4 times the width W. So this is 4W, and my width is W. What is the maximum length? We're talking this distance right here that can fit through the door. So again, we're trying to find the hypotenuse or a side length of a right triangle. So we use Pythagorean's theorem. Our legs are the two that make our right angle. And our hypotenuse is our longest side opposite of the 90-degree angle. Got to square there. Keep in mind, both of these pieces get squared. It's our product property of exponents. So 4 squared is 16, and W squared is W squared. And that's because when we square something, we take it times itself. So it's 4W times 4W, which gets me to 16W squared. Now, if I have 16W squared and one more, I actually have 17W squared. To get rid of my square, I take the square root. 17 is prime, so in the last one I could have broken up to 10, but I knew that there weren't any perfect squares in there, so it didn't matter. Here, my W's I take out, and I couldn't have broken down my 17 anymore because it's prime. So W times the square root of 17. The division property of radicals on page 621 is very similar to our multiplication property in that we can write radicals by dividing them as 2 separate radicals or as one radical with division, which we would write as a fraction. So in example 5, I can either keep this as 1 square root with a fraction in it, or I can write it as a fraction with both pieces as radicals. So instead of having the square root of a fraction, I can have a fraction of square roots. And this is helpful because we know that the square root of 64 is 8. And we know that the square root of 49 is 7. So we can simplify both of those individually. On B, however, if we look here, they're not perfect squares. So it's still going to be helpful to reduce our fraction first if possible. So 8 is the same as 4 times 2, and 4 is 2 times 2. So 2 times 2 times 2 times x times x times x. 50 is 25 times 2, which is 5 times 5 times 2. And we have 1x. Now here, because we have a fraction, I can cancel things out. 2 divided by 2 is 1. X divided by x is 1. And 1 times anything is itself. So what I actually have left in the numerator is 2 times 2 times x times x. And in the denominator, 5 times 5. I can write these as two separate radicals now. And when I have my separate radicals, I can look for any groups. Right now I have a group of 2's. In my numerator, they come out as a group of 2's. I have a group of x's. In my numerator, they come out. And since they started in the numerator, they stay in the numerator. I have a group of 5's. Those come out. And since my 5's were originally in my denominator, they stay in my denominator. So for a final answer, I have 2 times x in my numerator, and in my denominator, I have 5. So 2x over 5. Now, what is the simplified form of each radical expression? Feel free to pause here and give these a try. 144 and 9 are both perfect squares, so you can either reduce this right away if you want to, or we can split them up into into individual square roots and then take the perfect square. So the square root of 144 is exactly 12, and the square root of 9 is 3. Now we'll reduce here further. I can take a 3 out of both of them, and 4 over 1 is just 4. Or I could have taken 12 fractions as the same as division. So I could have taken 12 divided by 3 and gotten to 4. In B, our numbers are perfect squares, but we also have those variables there. So to make sure that we simplify those right, sometimes it's helpful to simplify first. So 36 is 6 times 6. 6 is 2 times 3. And 2 times 3. And I know I did that factor tree upside down, but that's just because of space here. 2 times 2 times 3 times 3 times a over 2 times 2. And a cubed. Now, anything divided by itself is 1. Anything divided by itself is 1. And anything divided by itself is 1. And 1 times anything is itself. So right now I have the square root of 3 times 3 over a times a. I can split that up into two separate square roots using my division property. And now I can look here and I can say I have a pair of 3's, so I take that out as a 3, and a pair of a's, and I take that out as an a. And because my 3 was originally in the numerator, it stays in my numerator. And because my a's were originally in my denominator, they stay in my denominator. So here, 3 over a, I have nothing left inside my square roots, so I don't even have to write a square root. If I look here, guys, there's nothing that I can simplify. If you're not sure, though, we can write it all out. So 25 is 5 times 5 y cubed over z squared, so z times z. I can't simplify anything, so I'm going to split these up into two separate radicals. 5 times 5 times y cubed over z times z. Now I look for any pairs if I can. I have a pair of 5's that come out as a 5, a pair of y's that come out as a y, and a pair of z's that come out as a z. Keep in mind they stay in the same part of their fraction as they originally started. So my 5 and my y were in my numerator, along with I have a square root of y left here in my numerator. In my denominator, I just have a z from that square root of the pair of z's. And that stays in the denominator since it started in the denominator. When a radical is in the denominator of a fraction, or a radicand is a fraction, we need to rationalize the denominator, and that means removing the radical to make a rational number. To do this, we need to multiply the numerator and denominator by the same radical expression that makes the denominator rational, usually by finding a perfect square. Again, Irrational are things like the square root of 5, square root of 17. Things that are square roots of things that aren't perfect squares. So what we're trying to do, guys, is get a perfect square, because then we can take it out as a pair and no longer have a square root. And again, that's just in our denominator that we worry about it. We don't want to have a square root in our denominator. So in example 6 here, we're going to try and rationalize our denominators. We're looking for the simplest form of each expression. So in A, there's nothing I can do with a 3 and a 7 to simplify. So what I need to do then is to try and get my denominator to no longer have a radical. And I do that by multiplying it by another square root that will make a full pair. So right now I have 1 7. The only way I can take that 7 out of my square root is if it's in a pair. So I need another 7 in order to make a pair. And whatever I do to the bottom of a fraction, I have got to do to the top. So since I multiplied the bottom by the square root of 7, I need to multiply the top by the square root of 7 as well. Now, square roots, when we multiply, I can multiply my radicands inside one square root. So in the top, instead of having 2 separate square roots, I have 1. And in the bottom, in my denominator, I also just have 1. And now, I can take that pair of 7s out. So all I have left is the square root of 21 over 7. And again, we specifically picked the 7 because that's what we needed in order to make this 7 into this perfect square combo. So if I look in B, again, the first thing I always want to do is reduce if possible. So square root of 7 is just 7, but 8 is 4 times 2, and 4 is 2 times 2. So here I have the square root of 2 times 2 times 2 times n. I can take this pair of 2's out as a 2. So now I have the square root of 7 over 2 square root. I have a 2 and an n left. And because that 2 came from a pair of 2's in the denominator, it stays in the denominator. Now, I don't want a square root in my denominator. So in order to get rid of it, I need to make a full pair of 2's by multiplying by another 2, and a full pair of n's by multiplying by another n. And whatever I do to the bottom, I have got to do to the top. So in my numerator now, I have 7 times 2 times n inside my square root. In my denominator, I have a 2 outside my square root. And inside, I have 2n and 2n. So I can take out a pair of 2's as a 2 and a pair of n's as an n. And now there's nothing left inside my square root, which is perfect. I don't want a square root in my denominator. So my final answer here, 7 times 2 is 14, n. Inside my square root, outside my square root in the denominator, 2 times 2 is 4, and I have that n. And again, I can't multiply or divide something that's a whole number with something that's a square root. They have to either both be square roots or both be whole numbers in order for that to work. Here, the 2 and the 3 I can't simplify. So I need to make full groups in my denominator. Right now I have 1 3. I need a pair of 3's in order to be able to get rid of that square root. So I have to multiply by the square root of 3 over the square root of 3. That's the same thing, so it's really just multiplying by 1, and we know that we can do that. So however I change the denominator, I also have to change the numerator. So in my numerator, I have a 2 times 3, and in my denominator, I have the square root of 3 times the square root of 3, which is perfect, because now that pair of 3's can come out as a 3, and I end up with the square root of 6 over 3. I have no more square root in my denominator. Again, reduce first where possible. So right now I have the square root of 5 over the square root of 2 times 3 times 3 times m. Pair of 3's can come out, and since it originally started in my denominator, it stays in the denominator. Now, I have a 2 and an m inside my square root, and I don't want any square roots left, so I need to come up with complete pairs. Right now I have 1 2, I need another one to make a pair, and 1 m, I need another to make a pair. However I change the bottom, I have to change the top. So in the top, I get 5 times 2, 10 m. In the bottom, pair of 2's, pair of m's, so 6 m.